Safety Plus laboratory, and he's going to tell us about security in mobile phones. Those of you who worked on this know it's terrible, and he's going to tell us interesting stuff. Okay, thanks very much. Good afternoon. Thanks very much for being here. I know that on a Saturday, almost 4, it's a good time for a nap, but I think the talk is going to be interesting enough so that you postpone your nap, your siesta, till the next talk. Okay, I've been introduced as a mathematician, but do not worry. I will not do like Raul. I'm not going to bring here any ciphering. Right now, I work for A Plus Laboratories as safety in the area of safety. And although many of you will know A Plus as a certifying entity, the truth is that we work on software and hardware assessment. And among the products we assess are the trusted executed environments. Structured execution environments. And we decided to present this talk because analyzing other talks on the TEE issue, we realized that there wasn't enough emphasis made on TEE, what it offers, what advantages are there to its use. And our idea is to answer those questions and analyze as well vulnerabilities in the TEE's designs. I think this will be useful as an introduction to this world, but many things will be left to say because we do not have as much time as I would need to explain everything. So I'd like to start by explaining why TE appears. Probably many of you might know what a secure element is, but for everybody else, a secure element is a highly protected chip
on which we execute an OS and to which we delegate cryptographic operations, and they may also be used for storing important assets in the system. So where do we find these kind of chips? On credit cards, TPMs, or even in new IDs 3.0 from the Spanish government. And these are basically hardware solutions, where protection is in hardware. Regarding software, what do we find? One of the most extended and similar security elements is the hypervisors and the whole world of virtualization, where we can find applications such as the host card emulations or the OS, such as Android runtime. In this battle between hardware and pure software solutions, we need to locate the trusted execution, the TE. The trusted execution environment, TEE, which combines hardware and software. Regarding software, we need to think that a device that uses a TE will execute at least 2 operating systems in parallel. One of them is a rich operative system, and we need to think of that concept as our Android, iOS or Windows, and then the trusted operative system, where we delegate all those operations that are critical that we want to protect. So what do we need to understand by critical operations? Key generation, data ciphering, but also the verification of a fingerprint. And all this software layer requires hardware elements to give it properties such as isolation or secure start. This may be totally new for some of you, but in fact, many of your devices that you have here nowadays are using a TEE already. In fact, maybe you have already interacted somehow with a TEE. There are applications such as Touch ID or Samsung Pay delegate part of their services to the TEE. But we mustn't think that this is just exclusive for smartphones or tablets. Everything we know, such as IoT devices, are also using this technology to protect a part of the system's assets. We shouldn't be surprised if the next intelligent fridge or smart fridge we buy protects our shopping list within a TE. And now that we're a bit more aware that this is something quite noticeable and tangible, I'd like to be like a surgeon to explain what the inside of these kind of products is like. And I'll begin talking about the hardware. Regarding design, we need to think that fortunately there isn't a single valid design. The pointer doesn't seem to be working. Well, it doesn't matter. Demo effect. Any of these three designs, for example, if it allows us to have an isolated execution environment from the rest, and an interface through which we can delegate the operations we define as critical, might be perfectly valid. Maybe some of you are thinking, well, the Type A model looks like the secure element concept. In fact, regarding design, it looks like a secure element. But in this presentation, we'll see that we require some characteristics from the TE that differentiate a secure element from a TE. But please bear in mind the Type B model, because that's the design where the trust on technology that we'll debate next is based on. The main feature of this design is that the device resources are split between the exclusive use for the TE and for the rest of the device elements. So trust zone, if you know about TE, you've probably heard about trust zone, is the main hardware technology to use a TEE. And it is the main hardware technology because most devices we use ARM processors. And this technology has been designed for or by ARM. There are other technologies such as Intel, and they implement the Intel SGX, which is equivalent to trust zone. But due to the large number of devices that use this technology, it's important to know at least how it works. Trust zone is based on the fact that the processor cores may be executed in two states: secure, that is associated to the processes executed in the trusted operating system, and the non-secure state that will associate to the processes executed in the RIT operating systems such as Android, iOS, and so on. These states of the processors are represented in a bit that is stored in a register called Secure Configuration Register, or SCR. And when that bit equals 1, it refers to the unsecure state or non-secure state. When the bit is 0, it refers to the secure state. And if we research here, we'll see that we refer to that bit as a non-secure bit. For whoever who may not know about this, this is the execution mode chart for a ARM processor. And in the last line, that's where the magic happens. So how does the processor get into this level 3 of monitor mode that we saw earlier? The standard way is through instructions called secure monitor call, and the kernel of the operating system will execute that. The other way is through system interruptions. And once the processor reaches this level 3, there is a module called secure monitor that does the state change, and that is within the trust zone firmware. The part that might be very interesting is that the source code of this firmware is public, and you may find it on GitHub without any problem. However, it's important to bear in mind that whenever the processor core reaches the secure state, it will have access to all the resources of the device. Thus, the importance of having a robust design for the TEEs. So far, I've talked about the processor. If you may remember, the design on which the trust zone technology is based allows to split the resources of the device between those exclusive for the TE and those for the rest of the system. To do so, we'll need some controllers that are specific hardware controllers that allow us to filter transactions, looking at the state of the processor. And this is useful in topics related to configuring internal and external memory regions that are for the exclusive use of the TE, and it's also useful for peripherals. We can mark peripherals that are only for exclusive TEE access. In peripherals, not everything is either black or white. Just imagine the case of your device screen. We're not always using the screen in critical activities. Sometimes we use it to watch a video or to read something in the newspaper, but other times, like when we type a password, we like the TE to manage these kind of peripherals. Therefore, we'll need hardware controllers that in execution time are able of changing the state of the peripheral. Sometimes we have no other choice than allowing for this type of flexibility. And here we have the internal SoC diagram that uses this technology. I don't expect you to understand every single thing that appears here. It is important, however, to look at the parts that are marked in red. I refer to those specific hardware controllers that appear to be able to filter transactions according to the status of the processor. I do understand that this image of the samurai warrior may be shocking, but it's quite easy to visualize here which are the parts of a samurai warrior armor. No matter how small a part may be, if that part is lacking, the warrior will be in advantage in the fight with an opponent in a battle. And something similar happens with this technology. If you use one single component of the ones we mentioned, no matter how small it is, we're actually opening a hole in the system and we're not protecting it fully. And I can assure you that more than one of these devices I mentioned at the beginning that are using TE, and that you're probably using, do not have the full armor. you'll be able to assess this table later on with the slides. And this is just a summary of what we've seen so far in this trust zone technology. And it's important to highlight that the middle column refers to application processors that we use in our phones, and the last column refers to microprocessors that are usually more related to IoT devices. Okay, so to finish with the hardware part, I'd like to talk a little bit about the safe or secure start mechanism. As we've seen, hardware needs higher layer elements such as firmware. No matter how well designed and robust the pure hardware part is, if we don't have the security and the trust and confidence that the firmware we're executing is the one we want, the whole system will collapse. Therefore, it's necessary to use this secure start mechanism. What's all that about? Well, we need to begin with a trusted source that we call root of trust, and that's usually the image found in the ROM. Once it's started, the rest of the system images will initiate until we get to the user's operating system image. And in each stage, we'll need to verify the signature image to check its authenticity and integrity. This is not just an exclusive mechanism for TEE solutions. However, it's important to highlight that this is one of the pillars where their security is based. And as I was saying, a TEE has hardware elements as well as a software layer. Regarding the software, on the one hand, we'll be interested in the trusted operating system. And here, we're interested in everything from the trusted applications, that are the applications executing this operating system, as well as in the rest of the components. We'll also be interested in certain elements of the current operating systems, what I call the client applications, which are the applications that will use the services provided by the trusted applications, as well as the rest of the elements in the operating system that allow for the communication between the client application and the trusted operative system. So in my opinion, which are the strengths or benefits of this new software layer, where instead of having one operating system, we have two? Well, the trusted operating system will be a reduced operating system that we access in a very controlled way, where we can delegate all the critical operations. On the other hand, regarding marking the peripherals are secure, in this trusted operating system, we can delegate drivers management. Therefore, we can talk about trusted peripherals. And last, that isolation property isn't just happening between the two operating systems, but in fact internally within the trusted operating system, we'll want to execute applications in an isolated way so that no other trusted application may have access to resources that are assigned to the other trusted application. And I think that this is more clear in this chart, where we may see what happens, in fact, in a device executed by the TEE, where we have the two operating systems. When you take into account the trusted operating system is something that we don't see. It's being executed in background. On the other hand, even though I've mentioned that these are two isolated operating systems, the isolation is not complete. On the one hand, we'll need a communication channel through which we can request things. For example, I need a password. We need a channel to ask that question. On the other hand, if you notice, we'll need a shared memory buffer, because whenever we request the password, a trusted application will generate it, and the public part, in the case of a asymmetric password, might be the object of desire of the trusted application. What we need to keep in mind is that the aim of this new model is that our current systems, such as Android, Windows, Linux, and iOS, are operating systems for leisure, while these are the ones called trusted operating systems are the ones that carry out the hard work. And I think that we'll better understand this idea with an example. So here we have a possible payment app model within AT. This is a simplified model, but I think you'll understand and visualize quite well which operations should be delegated in the trusted operating system and which components need to be controlled in this trusted operating system. So let's think, or let's say that we're going to pay something. We begin the transaction and payment authorization is required. Since we consider this a critical application related to a trusted application, let's say that the fingerprint sensor is trusted, so the driver is managed by the trusted operating system. We request fingerprint from the user, and once we have it in the database, we need to check that that fingerprint really belongs to a user that has permission to make the purchase. If everything is okay, we'll need the appropriate token, and we'll generate a cryptogram that will send back to the user operating system so they can continue the transaction out of the device. As you may see here, this is not a full payment application model, but we can visualize quite well which elements we'll have and which operations will need to be delegated to these new models with two operating systems. And to finish with this software part, I'd like to mention that fortunately there are possibilities to work with free operating systems. In this case, OPTE with a public code in GitHub that may be useful to develop the software layer of ATE. And I mention this project because I think that it has a very active community, which is something quite important when we refer to open source projects. And since it doesn't just depend on software, but this type of solutions also need some hardware, there are several platforms that support being able to execute this operating system. Okay, so could there be a security conference where we don't talk about vulnerabilities? Of course, no. Believe it or not, different vulnerabilities and problems have been presented in the last few years related to TEE products. Most vulnerabilities found are related to errors in the code that led to intelligence overflow, entry parameters errors, and there have always been problems in the TEE design. Personally, the second type of vulnerabilities of problems is the one I'm most interested in. It is arguable, but to some extent, an error in the code may be solved. However, an error in the design may lead us to fully discard the product. And next, I'll show some of the design problems that seem more interesting. And some of these problems come from the daily work. A piece of research on the TE of Qualcomm highlighted that the OEMs have the option of extending their own services on QSEE. Some of the primitives that the OEM could extend were things such as writing, memory reading, and memory copy, with the associated problem that through one of these new primitives, one of these memory regions that was exclusive for the use of TE could be vulnerated. And my question is the following. How come that the trusted operating system developer ensures certain properties when in fact they lose control on their system? Could it be necessary to extend certain services of a TE? Well, that should always be done in a controlled way. And mainly, we should never allow the modification or duplicity of critical services, such as the case of everything that regards memory. So what would happen if we have a TE with its trusted operating system, and also a peripheral, such as the fingerprint sensor, that it may not be managed by the TE? Well, here a malware that has access to our Android or our iOS will be able to compromise to some extent that peripheral. If we use that kind of device, it is clear that all the peripherals that may be critical must be managed directly by the trusted operating system. However, this is not enough. The communication bus existing between the fingerprint sensor and the TEE is not protected with this measure, and we could have an attacker that connects directly to the bus and obtains all the information. And here, other countermeasures may be necessary. For example, here we have Apple's example that deciphers the communication between the fingerprint sensor and the TEE. Last year, a piece of research was presented on the cache memory management in processors that use trust zone. And through this piece of research, it was discovered that these processors are not using the flash function in the cache. And even though it's not possible to have direct access to the cache memory set as for the TEE usage, they were able to recover the AES code in the cache memory through timing attacks. These are complex attacks, but this highlights the eternal problem existing between performance, cost and security, because eventually not having or not carrying out that flash operation is only done to improve the times in the changes of state in the processor. It is funny though that, if you remember, I talked about another hardware solution, which is Intel SGX, and this solution also presents a similar problem because it's vulnerable to timing attacks in the cache. I don't know which of you know how side channel or fault injection attacks work. In case you don't know, these are hardware attack techniques used mainly or to a large extent to assess the security of our credit cards, for example. So how does a side channel attack work? Let's say we have a chip that may carry out ciphering cryptographic operations. We have a message that we want to cipher through that chip. The first thing it will do the chip is to load the ciphering key, the appropriate one. We transfer a message, and if everything goes okay, we'll get a ciphered text. Okay, so if we're able to assess the temperature, the electrical consumption, the electromagnetic frequency of the device while this cryptographic operation is being carried out, we could actually obtain the code or the key with which our message has been ciphered. So what happens in the case of fault injection? Let's remember the same thing. We have a text that we want to cipher. We have a chip that carries out those operations, and we may obtain the cipher text at the end. Well, if we apply mechanisms that disturb the functioning of the chip, for example, through laser glitches and similar things, and we assess the result after disturbing the chip, we might be able to obtain a cipher key or any other thing that we want to achieve and obtain. So we just thought about testing these kind of attacks on a plate or a board that uses trust zone technology, and on which at the operating system level for trusted we have the OTE.
Although it is true that this type of boards are general purpose boards that do not implement physical measures in terms of hardware or at hardware level against this type of attack, on the one hand there are countermeasures at the software level that can make it difficult or even impossible an attack of the nature I've mentioned, but also at the technical level. And for us, compared to a secure element, this type of processors have features. They are, for instance, multi-core, multi-purpose processors that also make the analysis of this type of attack harder. So we decided to try and see what happens. Would be missing here some anticipation device with music or drums or whatever, but what happened was that we managed to breach the implementation of RSA with a fault injection and side channel attack in the platform that I've mentioned. It is true that, as I was saying, it doesn't make much sense to adopt hardware protection mechanism, but at least software protection mechanisms that at least make this type of attack harder, because we don't know who our adversaries are, and it's becoming cheaper and cheaper to do side channel attacks. At this point, I'd like to thank my colleague Nuria Carrió, that I am here talking about it, because she is the one who's put it in practice, and I think she deserves the recognition. And finally, before TEE, there were different protections to protect system assets. One of them are replay protected memory block, and these are partitions that exist in our flash memory since 2011, and where the writing and reading operations have to be done in an authenticated way. So what happens if we want to store critical assets in those partitions? Well, we either cipher that information beforehand, or these do not protect confidentiality. And why do I say this? That may seem obvious. Because even the TE is being used, although it is being used by the TE because it's not an exclusive measure, we do not know if there's another application who also has the key to do authentication operations on those partitions. And to finish with this part, I decided to list some of the recommendations that could be used by somebody who wanted to design a TE. And perhaps with all the information that I'm giving today, perhaps next year in the router, one of you will be here presenting your development of a TE. At any rate, keep them in mind in case I have to assess your design, so I don't have to scold you for not listening properly to me in the router. So after this talk, which is perhaps a bit dense in terms of material and content, you may be wondering whether this technology is really worthwhile. In my view, it is technology that's halfway between secure elements and exclusive use of current operating systems that we've seen on their own do not offer enough protections. It's true that compared to a secure element, they do not have so many protections at the hardware level. They do offer some functionality such as protection or adding a security level on top of peripherals, which it's impossible with a secure element. On the other hand, at the level of costs, most of these devices, processors that use ARM, they will allow us, at least at the hardware level, to implement a TE. So we won't have to spend a lot of money. And finally, it may be surprising to some of you, but due to its architecture particularities, TE is being used for purposes such as sandbox environment for malware analysis. If you do searches in the internet, you will see some papers and some documentation about this. But of course, that's not the perfect solution. Although I have to say also that I don't believe that perfect solution exists. As to the problems that I think are more important to emphasize in these technologies, nowadays there is a huge shortcoming in terms of standardization, particularly in applications development. You will not be able to go tomorrow and say, I want to do a trusted application. As of today, that's not possible because it's too closed an environment. And then in terms of security, as I'm sure you will have realized, in order to have a TE, you need a lot of parts. And just like we've said with hardware, we will need all components because otherwise our armor is incomplete. We need to have the operating system. We have to be able to trust that it will not be delivered to a third party already tampered with, perhaps with the access API to that operating system. And I think that's also one of the problems. We do not know whether that TE you're using in your mobile right now, how has it been set up? And finally, regarding standardization, there's also a difficulty of hardware integration. I've mentioned at the beginning that the firmware code is open. You can access to it. And there are projects of trusted operating systems. They're open as well, but even if you have all of that, nowadays it's going to be very difficult to integrate all that in a real platform. Integration with hardware is very difficult, however much you've done your software development. I believe it is a solution that's here to stay. I don't think it's a passing trend. I think we will see it in more and more devices. It will evolve, I think. It solves some problems that were present in our current devices. What I like better about this type of technology is the peripherals management. The fact that they can be isolated from the fact that Android or iOS may be managing critical peripherals. But the great weakness is that in time it should continue to be a closed environment in which the sector won't allow any of us can choose to participate. Okay, I hope you enjoyed this talk. And above all, I hope I've been able to teach you something about what trusted execution environments are. And if you have questions now or later on, I'm willing to answer. Anybody brave enough? I do have a question. Have you estimated the overhead that trusted introduces in operations with Trust Zone? An estimate of the overhead that Trust Zone adds or any TE? We haven't done so, but we could do it if you're interested. No, I do not know. Okay, thanks. Okay, thanks.